Okay, so let me just start off, and initially I will motivate the application, and then I will summarize all what I have done, and then we will dig deep into a few topics. And so yeah, so the topic is propagation and delay optimal state messaging in vehicular networks. The final goal, not sure when, but hopefully someday, hands off, feet off, brains off, right? Okay. Okay, so the statistics that motivate most of this kind of work is, there's a significant percentage of accidents that occur because of distracted driving, and the idea is to, take away a little bit of control from the driver. And there are other benefits too. For example, better road utilization, less time spent on road, greater fuel efficiency. Okay, so just to give a brief introduction to people who might not know, intelligent transportation is not exactly a new topic, and I think the first thing in the US was around 1986, the California PATH program. But the one thing that really increased the amount of research in this area, especially the research that uses Wi-Fi-like radios, is the FCC allocating 75 megahertz in the 5.9 gigahertz band in 1999, right? And currently this project is called IntelliDrive. Actually, IntelliDrive is recently they stopped calling it IntelliDrive, but everything else remains the same. And there are lots of partners, GM, Toyota, and so on, that are a part of this project. Okay, so just to tell you a little bit about the basic network setup. You have these vehicles on road, and each vehicle has what's called the onboard unit, which basically consists of all kinds of sensors and also is connected to a radio device. And then you have the RSUs, which are the roadside units, and which basically are the infrastructure part of the network. In this work, I do not use RSUs in any way. We only think of vehicles with radios, and with the OBUs on them. Right. So as I said, we have Wi-Fi-like radios. It's a very similar standard to 802.11a at the file layer. That is, there are differences, but we won't worry about them. And yeah, what about the application types? There are various kinds of applications one can conjure up when you have radios on every car. But nevertheless, the applications that we will worry about are what we call safety applications. I'll give you more details about what kind of safety applications we are talking about. But there are other applications like traffic information, which in some sense we even today see, right? And so going further into safety applications, an example of a safety application is the intersection collision avoidance application. So you have these two cars, and they have their onboard units on them and their radios, and these two cars can exchange all kinds of sensor information to ensure that they basically pass the intersection without colliding with each other. Now, this exchange can involve an RSU, but as I said in my thesis, I'll ignore the RSU. Okay. There are various other possibilities: curve speed warning, emergency electronic brake light, and so on and so forth. Okay. So this is an example of a car that has all kinds of sensors, a very sophisticated car. And the question many people ask is that in case you have cars that have radars on them, why do you really need radios that message? So the answer to that question is that there are maneuvers that might last over many seconds, and because of those kinds of maneuvers, the vehicles that want to talk to each other or should be in contact with each other may not be in the field of view of their radars, right? And there are studies which actually show that messaging can actually help avoid chain collisions. Messaging meaning using radios over a long distance. Okay, and at the minimum, you would hope that these radios, even if they do not take away all control from the driver, they will at least be able to give the driver some assistance and warn the driver, before the driver makes any kind of a maneuver on the road, or help the driver make a safe maneuver. Okay.
Are you suggesting we're going to all have radars on cars?
No. So we will not require. I'm not sure whether we have radars on cars. We already have cars that have radars on them. But the kind of messaging we are talking about, the kind of applications we are talking about, require more than just a radar on the car. We require radios that can talk over, say, 100 or 200 or 300 meters, for example. Okay, so there are two kinds of safety messaging categories, and one is event-driven. This is what some people say will be the initial version of safety messaging. So if there's a car that's in distress, for example, car 2 here, say your car breaks down, so the radio on the car, hopefully it will survive and it will broadcast messages, basically broadcasting the fact that it needs help. And then a certain emergency vehicle can come and give the car whatever help it needs. And it's then that the car stops broadcasting the message. So that's the idea of event-driven messaging, right? There's another kind. Another thing to note is that in event-driven messaging, it's usually a one-to-many kind of a broadcast, right? Many people receive this broadcast, and although the intended destination is typically, it can be a given vehicle in a given geographic area, or it could be a group of vehicles too. Right? Usually, you're targeting a geographic region of interest. Okay. For the periodic safety messaging case, you have you basically have these cars that are broadcasting sensor information. For example, say a car is broadcasting the fact that it's going at a certain velocity or acceleration and so on. And the idea is that every car in the network will basically broadcast this information and will do it periodically, right? And as I said, for this thesis and for the rest of the presentation, we will not worry about any particular sensor information. We will just call all this sensor information state information, right? And the idea is that these cars basically broadcast state information periodically, right? And why is it a challenge? I'll go into the details further, but one of the reasons is that all this messaging is time critical. Okay, so before I really go deeper into any of the topics, let me just summarize what I have been up to for the time I've spent here. And there are two categories, two broad categories under vehicle-to-vehicle communications that I have worked on. And one of them is safety messaging. I did motivate that application to some extent. And under that, as I said, there is event-driven and periodic. So I actually started off working on safety messaging, with GeoMAC, which is basically a geo-backoff based cooperative MAC. And the idea then was that there are many people who are trying to apply routing schemes like AODV and GPSR and so on to this event-driven safety messaging problem. And as we show in our work, you can actually do simpler broadcast relay kind of schemes using some location information and actually get much better mean delays and even very small jitters in message delivery. So basically, GeoMAC was much simpler and much better than the typically used protocols then. Then we have periodic, and we'll basically chapters 3, 4, and 5 of the thesis. We'll look at periodic in much more detail, so I'll not spend any more time here. We have chapter 6, which basically was an empirical study which looked at how you can reduce the rate at which sensors need to generate messages. So a simple example is that of location. The fact is that cars mostly move in straight lines, so you should be able to predict, like other cars should be able to predict a given car's location. So if that happens, then cars do not need to necessarily transmit at the rate at very high rates. So we try to see what are the rates at which they need to transmit, so using GPS traces and so on. So as far as channel goes, I started off with a fairly detailed study of how placement of antennas can matter to the antenna pattern itself and its effect on the network performance, especially because what happens is that it leads to some kind of beam forming, and then that leads to hidden nodes and so on and so forth. So that's chapter 7. Chapter 8 is something I did very recently, and that is basically extending the effect of a car on an antenna and the network to the effect of multiple cars around a transmitter and a receiver. Okay. So the difference between chapter 8 and a lot of work that has gone into measuring the V2V channel is that in this we very specifically model the effect of other cars, and we use typical studies use DSRC radios, but we actually use we actually measure the channel instead of just looking at higher layer statistics like PDR. So hopefully our measurements can actually give you those measurements too, although the study is fairly limited in comparison to many other studies that have been performed. Okay, so with that, let me just dive into periodic safety messaging. And yeah, okay, so this is the basic challenge, and this is why this problem is interesting, is because we are dealing with large networks and because we require reliability and timeliness. Otherwise, frequent updates of 1 to 10 hertz are not that frequent. It's only because you're looking at hundreds of cars that there is a challenge. Okay. Okay, so just to motivate the metric that we will use and that we'll evaluate, think of it simple two-car network, and we have car U and car V, and basically in the ideal world, cars U and V would want each other's latest information, right? if there were no delays involved in transmission, in processing and all, you would want to, we would want to know what car use sense information is at a given moment. And at every moment it would want to know that, right? But that's not possible, and so what we define is we define what we call the age. So age intuitively is how old, so age of use information at V is how old use sensor information is at V. So car V has some snapshot of use sensor information. How old is it at a given time T? That is basically age, as clearly age is a time varying quantity. So delta UV of T is basically age of use state at V at time T. Okay, you want to take VD with time averages, okay, and that's basically delta UV, just drop the T. And then we have this delta UV is just on the link U to V, use information at V. But we are interested in networks, so we basically average over all such delta UV quantities, in this case 2 links. So that's why you have 1/2 into delta UV plus delta V. That's the system. Okay, you can very easily extend this to a network of n vehicles, and you get 1 by script n, which is basically n into n minus 1 links, because those many links exist in the network. Look, remember that these links are not wireless links per se, they don't have to be, they are application to application links. So the application at U connected to the application at V. So those are the n into n minus 1 links here. So we are assuming that these n vehicles want to talk to each other. Okay. Okay, so we look at two two ways of minimizing system age, which is the network code. So basically, intuitively, you want to minimize the average age of information any car in the network sees from other cars. That's the intuition. You want the information to be as fresh as possible at the cars in the network. Okay, that's what the system age, minimizing system age does. So we look at single hop CSMA networks. That's the first part of the presentation. And in single hop CSMA networks, we will look at application layer rate control to help us minimize age. Then we look at multi-hop networks, wherein we will look at optimal round-robin schedules and optimal piggybacking. The difference between these two works is that the first work is actually something that can be, at least in certain scenarios, can be used, can be deployed in practice. The second work is mostly to understand what the possibilities are. How much better can you do? Okay. And in both works, of course, we will look at large networks. Okay, so with that in mind, let's go to single hop broadcast. Okay, so we have a fully connected network. This is kind of we assume that the wireless channel is perfect. This is just to make life easier. And basically, all cars can decode the messages of all other cars. So there never is a packet error because of the wireless channel. Of course, packet errors can take place because of high collision rates, which are a feature in large CSMA networks. So when I say CSMA network, you're using 802.11 kind of a protocol to access the channel. The other peculiarities of this problem are that since all these messages are broadcast, a message that any car sends should be received by all cars of interest, which is all cars in our network. No ad-based feedback is available. It's not that you cannot engineer an ad-based feedback, but you do not want to because this is anyways an interference limited setting. So you do not want to introduce more messages. Okay, so the point being that the transmitter does not know who did or not receive the packet, and the transmitter would want every car to have as fresh as information as possible, but it has no idea of what happened to its message. Okay, there is related work, and I'll just breeze through these two. And a lot of work tries to achieve, tries to basically enable periodic messaging in these kind of networks, in large networks. But these two works, what they do is that they basically, in summary, they try to reduce the load that a given car sees. Load meaning the load on the wireless channel. Okay, and you want to reduce it to such an extent so that you actually see the kind of delay performance you want to see. And the way you reduce it is you reduce the network size, and you do that using some kind of power control. Right? So in our case, as I will say, in our work, what we do is, other than the fact that we use the metric of system age, which is kind of new in the domain at least, we also say that the network of cars is the network that wants to talk to each other. Okay, we do not reduce the size of the network, but we say that since you cannot broadcast at any rate for a given size of network, you really want to select a rate. You want to select a broadcast rate, which will help you to minimize the average system age. So we are keeping the network size constant, and we are doing some kind of application message rate control. Okay, and reducing range is not an option for us. Of course, in general, you would want a mix of these two schemes, but here we will just go with this kind of framework. Okay, so just to show again how time varying, how age varies. You have car 1 and car 2. Car 1, the application, and this is important. The application at car 1 generates state packets, okay, which might contain all kinds of sensor information, right? This packet, after it goes through all kinds of delays, say queuing, backoff, transmission, right, is received by car 2, right? Once car 2 receives this packet, the age of the state in car 2 is basically the horizontal black arrow that you see, right? Because that's the time the sensor information in this packet has spent in the network before it was received by car 2. Okay, so that's what your age gets set at car 2, delta T12. Okay, so when packet 2 is received, the green arrow with 2, the age gets reset to how much ever time packet 2 spent in the network, right? In between reception of packet 1 and packet 2, just as all of we get, just as is the case with anything that gets older, the age increases linearly in time. Basically, the information is getting older with time, right? All right, so okay, and so the takeaway being that the age gets reset when a packet is received. The value to which it gets reset depends on how much time that packet spent in the network. The other reason why the age can increase is because of absence of packets. So if you're not receiving any packets, age increases, right? So queuing, backoff, transmission, this decides the amount of time a packet spends in the network. Packet arrival delays basically depends on what is the rate at which an application is generating packets. Okay, so what we are interested in averages. So since a lot of this work is simulation based, the averages are time averages, which basically means the area under this curve normalized by the observation interval, which is script t. Okay, so just to give you some intuition about what the system age is, consider a very simple system, an MM1 system where you have an arrival rate and you have a service rate. You are basically given the service rate, and this is your application generating packets at an arrival rate of lambda, right? And we know that if I increase lambda, if I make it close to mu, right, I will basically have very long queues, but the throughput of the system will be maximized. The result of having very long queues is that your system age will increase because packets will spend more time in the network before they are received, right? So packets will be older. On the other hand, if I want to reduce the time a packet spends in the system, if I want to reduce packet system delays, then I would want to make lambda as small as possible. But that would really mean that hardly any packets are being generated by the application, which again would mean that the system age becomes very large, right? So basically the intuition is, and maybe if I get time to present future work or the work I'm currently doing, I'll tell you what the exact values are. But the intuition is that the system age must be minimized at an intermediate arrival rate. You don't want to maximize throughput. You do not want to minimize the delay a given packet suffers. So that's one difference between system age and the typical network metrics that we use. Okay, this is the network of our interest. There are we did simulations for 50, 100, 200, so on and so forth cars.
Perhaps I've missed. What is your service?
Okay, so the service designing. So we don't use that abstraction of service in the work I do. But in the case of a CSMA network, you could argue that service would involve the time spent in backoff, the time spent in transmission and propagation. But it's more complicated because you have a network of nodes and every node has its own server to sit. But again, they are not independent of each other, the service times. Okay, so this is the this is the grid we look at. The grid is not very important really. What's important is that we are creating this simulation setup where cars are as tightly packed as they can be on a road, that is, and the idea is to create an environment where collisions take place because of the high density of the network. Okay, so we'll look at two queue update strategies, and okay, so let's call them latest out and FIFO. That's first in, first out. FIFO is what's typically there. All radios today use some kind of a FIFO queue at the MAC layer. Okay, you have this broadcast application which basically queues state info periodically into this MAC queue, let's say. Okay, the packet that's at the head of the queue undergoes CSMA backoff, okay, and then undergoes transmission. While a packet undergoes all this, other packets basically stay in the queue, they wait in the queue, right? Okay. The important thing to note is that there are no updates to the state in a packet once the packet has been queued. So the application has no control over the contents of the packet once it has queued the packet. Okay. The latest out system is a system that really doesn't exist, at least now. And the idea is that in this case, the broadcast application actually has control over the packet just before it is ready for transmission. It's like in the CSMA sense, the transmitter is ready to transmit. It thinks that it has a vacant slot or vacant time available. The channel is idle, and just then the broadcast application updates the state information in the packet with the very latest. Okay. Okay. So that's latest out. Let's look at, this is the network overview. This is kind of trivial. You have all nodes that basically use one kind of strategy, either latest out or your FIFO. Okay. You run NS2 simulations, and basically let's go to the simulations. So you have this is for the FIFO system. You have on the y-axis you have the system age, which we carry offline based on the simulations we do, and we basically do simulations for different broadcast periods. For example, a period of 0.3 seconds, 0.25, 0.05. So pretty large to very small broadcast periods, right? And we do these simulations for different contention window sizes. So the idea of a contention window size, for people who might not be familiar with 8.11, is basically a larger size means that the probability of a packet being transmitted onto the medium is smaller. If the packet probably will wait longer. A smaller size would mean that a packet would typically wait for a shorter time before getting transmitted onto the medium. That is a packet that is undergoing CSMA backoff. So a smallest contention window typically leads to larger probability of collision for a given network size. Okay. So that's what you see in the red curve. If you look at the red curve, as the broadcast period becomes smaller, okay, more and more packets get ready for transmission at a very high rate. So as a result of which, this curve basically keeps going up. Basically, the system age keeps increasing because the rate of packet errors increases as the broadcast period reduces. Okay. On the other hand, for larger contention window sizes of 500 and 3772, you can see a flattening of the curve towards as we go to the left of the x-axis. The flattening is because of the larger wait times. You basically the queue reaches a steady state wherein increasing the rate no longer increases the effective rate of packets that's entering the queue. So basically, it doesn't really make a difference how much smaller you make the broadcast period. The effective input rate remains the same, and that's why you see a flattening of the curve. The important point to take is that you do not want to be in this region, in the very small broadcast rate region, irrespective of whether you have a small contention window size or you have a large contention window size. Because for a small contention window size, you have large packet collision rates. For a large contention window size, you have large queuing delays, which also lead to the packet collision rates flattening out, but still the delays are very large. Where do we see small delays? We see small delays, say for the red and the blue curve, around 0.25, a period of 0.25 seconds. That means the state application is generating a packet every 0.25 seconds. Right? If you go further to the right, you again see that you start paying a greater penalty for a large contention window size, and that's because further to the right, although there is no contention, although there are no packet errors or not much queuing happening, a packet ends up spending more time trying to doing CSMA backoff if the contention window is large. So you basically want to be somewhere around. If I keep extending the axis to the right, you will basically see that this line is basically a straight line with a slope of I think around 45 degrees, not 40, I think 30 degrees. Okay.
What's interesting is that your contention window is like hugely different, 15 and 500 for that range, and still you have the same performance.
So the interesting thing, okay, the same performance is towards the right of the axis, and the reason for that is that there are no queuing delays. Okay, packet more likely is going to find an empty queue. The only differences that then occur are because of the time you spend doing backoff, and those are the delays you see. Those are the differences you see between black and red. Now these delays also reduce because over a period of time, system age, as you go to the right, is more affected by the period of broadcast. Because the period is becoming so large and the rate at which you're broadcasting is becoming smaller and smaller, that's the major factor as far as system age is concerned. So everything else becomes very small in comparison. So these curves basically merge as you go to the right. Okay, so if that's clear, then we can go to the next slide, wherein this we can ignore for now. wherein we look at a latest out system and we'll see how it does in comparison to the FIFO system, right? So we have the same axis. We have on the y-axis we have the system age, and on the x-axis we have the broadcast period. And here's the thing: the red curve is the curve we saw earlier too, and that's for a large contention window size of 3772, and for the FIFO system. The corresponding curve for the latest out system is the blue curve that's below, blue curve with the diamond markers, right? So for the large contention window size, if you used a FIFO system, your system age suffered because of queue delays. But the latest out has no queuing delays, and the reason for that is the way we conjured up the system, wherein we said that the application can actually update the state just before the packet is transmitted. So any queuing delays the state information had suffered basically amount to nothing, because the information gets updated. That's the reason for the flattening of the curve. As you can see, the flat curve pretty much achieves close to minimum. So I'll tell you what the strategy is. What's the strategy you can use if you want to use latest out. Before that, however, look at latest out for smaller contention window size. It basically follows FIFO, and the reason for that is what matters when you have a small contention window size is mostly the packet errors because of collisions. Okay, so if you are using a small contention window size, then if you're on this curve, that is so the curve that's basically increasing as the broadcast period reduces, the curve on the very top to the left of the axis, that curve corresponds to contention window 15. Okay, and if you're using that, then you want to choose a period the way you would have chosen for FIFO. If you're using a large contention window size, you basically can just saturate the queue. You can ask the application to generate broadcast packets as quickly as possible, assuming it's a latest out system, and that's all you need. Right? And that's a summary of the next slide. There are various ways of going about achieving minimum age. One is you're using a latest out system. Okay, so this one small thing I missed actually. So the thing is, this flattening of curve is not a given. It only happens at what's called the optimal contention window size. So this is something that was derived by Bianchi in a very famous paper, and the flattening is not very sensitive to the contention window size. It's not that if you make it 3000, it will start increasing like the curve on top, but it's important to be around the optimal contention window size. Okay, for the latest out system. Okay, so there are two ways. If you're using latest out, you can use the optimal contention window size, and you can saturate the queues at every node in the network. Okay. Or you can, if you are either latest out or FIFO, you could actually use a small contention window size. That's the red and blue curves with the circles, but then you have to find the well chosen period. In this case, around 0.25 seconds, at which your system age is being minimized. Right. Okay, so what's the issue? Like, why is there more? What's next in this work? And the thing is that at least currently there is no hardware support for latest out. Okay, and there's also this issue of the optimal contention window size being a function of things like the size of the network. Right? And typically, the kind of support we have for optimal contention window size is you do not have fine-grained support for the size, and typically there are very few levels of contention windows you can really sell. Right? Of course, there is the added issue of knowing what the size of the network is, but that itself is not a very trivial problem. Okay, although there are many people who have worked on it. Okay, so let's just do FIFO. Okay, and the thing with FIFO was finding the best rate. Okay, and as this plot shows, again you have system age on the right and broadcast period on the x-axis. Right, we have different size networks: 50 cars, 100 cars, 200 cars, 400 cars. And for each car network, I am telling you the approximate broadcast period at which the age is minimized. So the periods are basically circled, right? And the idea is you want to achieve this age, and the point is that the next part of this presentation will be a rate control algorithm which will try to achieve this rate in a distributed setting. Okay, so you have an application message. You of course have state that I already said. You have time the state was generated, and you also have the broadcast period, right? And the rate control algorithm is always invoked at the end of a measurement interval, and in our work, measurement intervals don't need to be synchronized, although we assume that they are of the same length at every car, at every vehicle. Okay. This is a simple. This basically, this is probably getting hidden, but measurement and control at each node. So we basically measure average period and age. I'll tell you what average period is. I'll also tell you how age is measured in a distributed setting. And then after you have done the measurement for say 1 second, 2 seconds, or 5 seconds, whatever your measurement interval is, you basically invoke the rate controlling call. Right? Okay. So the average period is every vehicle is receiving broadcast from other vehicles, and in a broadcast a vehicle sends out, it basically also says what's the period at which its application is generating packets. So a node averages that period over all the packets it receives. Okay. In the part of the algorithm I'll show you, we will not be using the average period, but if you read the paper, you will see that we use the average period for the algorithm. Then the other issue is of age, and this is where things are a bit interesting in that we define the age where we said we are averaging over n into n minus 1 links. So this basically means for the calculation of this, every car needs not only to know what it has received, but also what other cars receive. Right? Because every car needs to calculate this locally, but that is not possible in this kind of a network. And so what we do is, this is something we just started using and it seems to work well, and that is we use what I call the local estimate a given node or a given car uses. And the local estimate averages age only based on packets that particular node receives or that particular vehicle receives. So you just have n minus 1 links to every node. Right? Okay, so we'll use this local estimate of age, and let's further look at one part of the algorithm that I'm presenting. It's fairly simple. You have just two things it does. It either increases the period, the application period, or it decreases the application period. For that, you basically use a factor, beta is greater than 1 in this case. And the idea being that it's basically it's very similar to a gradient descent algorithm. Fundamentally, it is a gradient descent algorithm, and the logic is very simple. If your previous action led to an increase in age, then you want to reverse it. So if you increased it previously, you want to decrease the period. On the other hand, if your previous action actually decreased the system age, then the algorithm assumes that you are actually descending in the right direction. So you keep decreasing the age till you keep reducing the system age. That's what it is. Okay.
What made you choose multiplicative factors rather than...
I just started with the network. I tried additive, we compared it with additive factors and they were much slower. And as far as convergence is concerned, like we did end up choosing a parameter value for beta, which actually gives you very good convergence. So it's kind of quick and it stays once it achieves system. It oscillates, but not very much. So I have those plots that are not a part of this, but at the very end, so I can show you if time permits those plots of how things matter with beta. But we also tried additive. That's not in the thesis, but we tried and we didn't use it.
If you choose the beta too big, you get instability.
So beta 2, yeah, you get instability. It converges very quickly, but then not converges, so to say. It reaches the region of system age, minimum system very quickly, but then it tends to oscillate or go around. So 1.05 is what I use. 1.1 was 1.2 was pretty bad. Sorry, 1.1 is what I use. 1.2 was pretty bad. 1.05 is very slow but very good when it comes to stability. Very slow meaning.
But somehow doesn't that depend on sort of the physical situation?
So I tried.
How many nodes?
I don't think it depends on how many nodes, because all these calculations are like very local to a node. But and I tried simulations over 50 to 400 nodes. So it doesn't depend on the node per se. Like whether it oscillates or not, or whether it stabilizes, doesn't seem to depend on the size of the network. But how quickly you for a given start broadcast period, how much time it takes to go to the system age matters, because if you have a very large network, a given period will mean more number of collisions, and you basically have to go down further to really reach the region where you achieve minimum system age.
So there's some kind of framing time between making the adjustments, right?
Yeah.
So if you make that bigger, you use some other beta or not?
Right. So I didn't fully get it.
So in some way, the beta, is it dependent on the size of this frame you use for making your measurements? And
Okay, so there are two parameters. One is the frame size, which I call the measurement interval, and the other is beta. So beta is not a function, at least the thing I have done, it's not a function of the measurement interval. But usually increasing the measurement interval gives you better system age estimates. So usually that leads to better convergence, and for a given beta, that is, it leads to better convergence, and you get closer to the system age. When you use a very small measurement interval in a congested network, what happens is that because of large number of packet errors, you might not receive enough packets to come up with a good estimate of the system age. So there are other parts of the algorithm that try to circumvent that situation, but If you only use this, then you will have a problem. You might not converge because you will not have good enough estimates. Okay, so this is a prototype evaluation that we did on orbit. I did many simulations. The results are in the thesis. And the idea is you start with the y-axis on the right is the number of cars in the experiment, and you start with 300 cars. Okay, and I set the broadcast period at each car to a pretty to a pretty small value. That's around, this is system A, the y-axis. The broadcast period was around 0.03 seconds at each car, right? And then that's a very large, a very small broadcast period, or a very large rate for this size network, right? And so you see a very large system age. So think about it, like your broadcast period is 0.03 seconds, so the system age is 0.5 seconds. So that tells you how much delays being introduced with all the packet errors and so on, right? But since the algorithm kicks in, you see this algorithm go down. The age basically reduces over time, and then it flattens out, close to flattens out, till of course cars in the network reduce, right? So the thing is, whenever the cars in the network whenever cars leave the network, right? The cars that are still a part of the network do not know that they are going to leave the network, right? So the other cars that are still in the network and are still calculating the system age metric basically assume the presence of these cars that have left. So basically they start assuming that these other cars are transmitting, but their packets are not being received. So as a result of which, you end up with system age accumulating till you start the next measurement interval, wherein all cars basically reset all information they have. And so the very next at the end of the very next measurement interval, you again start descending towards the optimal or the minimum system age, right? So the important thing to remember is that because of the lack of information, there is a small period of time where the cars are being a bit more conservative than they need to be. They are broadcasting at a smaller rate at a smaller rate or a larger period than they really need to be. But as you see, like, the algorithm does tend to converge fairly quickly. We started at an age of 0.5, and we basically ended up at a very small age of 0.03. Of course, the network size also went from 300 to 50 cars. Okay, the interval setting for this was 5 seconds. Like 2 seconds on orbit really was very difficult to get to converge. Factor was 1.1. All these parameter settings are based on many simulations and experiments I did. There is no real theory behind them. Okay, so if this is clear, then I'll just go to the next question of my thesis. And okay.
This is John. This might be a good time for me to just say that the voice quality has sort of deteriorated as we've gone on here. So
okay, so
I'm getting most of what you're saying, but I don't know if there's anything we can do about that.
So I can
I can't hear other questions.
Okay, so I can probably try to repeat the questions, and I guess I'll just sit and present, so that way the mic will be closer.
Should we try the regular telephone?
We can try that.
That's much better. I don't know if that.
Yeah.
We can do that. Much better.
Yeah.
I don't think you can call from that one. You can call from this is comfortable.
Shut up.
Why?
Okay,
Somebody else soldering iron?
we'll just get the other phone, I guess.
It's not the phone, it's the cable.
Yeah, the cable is. Yeah, we need the cable. But this cable isn't connected.
So is the cable, it's not modular at the end of the phone?
Yeah, it is. At the end of the phone, it is. I have to remove that.
I guess it's going to be funny.
Sanjit, why don't you continue? John will try to figure it out over the next couple of minutes.
Thanks, Marco. I think I can hear better with the adjustment of Sanjit.
Okay, so just to summarize the thing I just presented, we basically proposed an evaluated system age for large CSM networks. So and various other things, but the limitation of there is a certain limitation here that needs to be mentioned, and that is in general the way this network is set up right now, all cars are connected to each other, can listen to each other. So the good thing about that is that every car on average sees the same kind of links. Right? But if you have scenarios where there are hidden nodes where there is a possibility of capture, that no longer remains true. So in that case, you might need additional information to go over the wireless channel, like who are the neighbors and so on and so forth, to ensure that the system age actually converges to its actual value, to its actual minimum value. I think the port is there. There's one here. Okay, so this is like this concludes the single hop part of periodic safety messaging, and let me go to the next question. And this part of the work is more to understand what the possibilities are. How small can you make system age if you could do whatever you wanted to do, basically. So the question is, what if we could engineer an arbitrary wireless network over a given physical road network? So you still have the 4 lanes, you still have the same cars, let's say, but now you're not really restricted in what kind of a wireless network you could design over this physical network of cars. And the question we want to answer is, can multi-hop broadcasting, if you basically engineer any network other than a fully connected network, it ends up being a multi-hop network, can that reduce or can that lead to a smaller system age? Okay, so with that, we assume round-robin scheduling. Of course, it's very, very difficult and almost impossible to do this in a real vehicular network, but we do this because we want to eliminate penalties suffered due to randomized access. So there are many penalties we suffer just because of the way CSMA is, and in fact, the CSMA that DSRC uses is not exactly the optimal kind of CSMA either. But anyway, the other reason is that assuming that safety applications always want to send a message every time they can, round-robin scheduling is kind of optimal. That's one reason why we are okay with round-robin scheduling. And then, of course, we also want to concentrate on mechanisms that lead to accumulation of age in multi-hop networks. So we will see that these assumptions about round-robin scheduling and so on and so forth make life a bit easy. So did you have to pause?
Is it beeping?
Can you call out this one?
No. They can transfer.
656.
Good luck.
So John, okay. Maybe we should do it for the question.
John, I'll email you a phone number.
John, can you hear us?
Can you hear?
Yeah, I heard some of that. What did you say?
Oh, so Marco is going to basically send you the phone you need to contact via email. He's going to email you the number.
Yeah, I think 6%.
So I think maybe we should just. I think this part of the work is something even I don't think John has seen any of it. So maybe we should just hold for 2 minutes. So in the meantime, I can answer any questions you have.
Sanjit, there were 3 lines going down in that plot. What were those?
Oh, so they were percentiles actually. So if you look at, this is the blue line is the median. Okay, the black and the red I think are the 90th and 25th percentile. It's just to show that actually this percentile there is this variation because there are some 10 or 12 nodes that behave in very weird ways. So but I thought I should show the entire thing.
So I see the implementation goes only to 300. Doesn't go to
Oh, that's because only 300 switched on the day that I did it. So. Maybe I should switch out the mic. Or what we can sometimes. Hey John.
Excellent.
Yeah, I think we can now. You can hopefully hear me better now. Okay. Great. Yeah. Okay, so let me just demotivate this thing. So the idea is that we look at the single hop setup and we ask the question. We did various things to achieve the minimum system age, but now suppose we have the liberty of engineering a wireless network of our choice. Okay, what's the best we can do? Like what better can you do as far as achieving a smaller system age is concerned? And that's the question we'll try to answer. Okay, so the idea behind using round-robin scheduling is it makes analysis really easy, and the other reason is that optimal scheduling for safety applications, if you could really do round-robin schedules, they are the schedules you would want to do instead of CSM. Okay, and it also helps us to concentrate on mechanisms that actually lead to accumulation of age or delay, like other than mechanisms that can be reduced if more optimal things are used. For example, packet errors because of medium access. Okay, system model is very similar actually. The only difference is that now we have a slotted system, and the slot length is basically tau seconds. Okay, and we again have delta T UV, which is basically a time varying quantity, which is age of use state at V at time T. Note that a packet that's sent by a node is a certain, it basically is a certain slots long. So the packet sent by node U is say L subscript U slots long. So when the packet is received by car V, the age of state information at car V is LU slots, because that's the time the packet spent getting transmitted. Okay. So with that, other thing is that if you're creating a multi-hop network, you have a situation where not all cars are listening to all other cars. So you want mechanisms by which cars relay other cars' information to those cars that are disconnected, right? And so we need piggybacking. So basically, the general packet now looks like a single header, which basically doesn't change much. A state, the state of the car that's transmitting, and the other states that this car will piggyback, so that these cars, as the states of these cars wouldn't otherwise reach all cars in the network, right? So header H slots, state S slots, packet length is just the header plus how many other states are being sent in the packet, right? Okay, so one of the reasons why piggybacking has been of interest to the community is also because in typical packets your header size is actually significant, especially it's much larger than the payload size. The payload is basically where the state information is. So your total size is 262 and your payload is only 53 bytes. Okay, so that in a way can motivate piggybacking to reduce network load, for example.
So why is the header so large?
Header has things like authentication and stuff.
Oh.
I'm not an expert in that, but it ends up being so large. Okay, so we'll assume a graph connectivity model. In that, we'll basically assume that either it's a 0-1 connectivity model. Either a car receives from another car or it doesn't, right? And in a real system, the assumption would be similar to assuming that you're employing really strong coding, right? Okay, so yeah, connected nodes decode all packet transmissions, disconnected ones do not. And this is a simple graph. This is not how a Baker network looks, but nevertheless, just to motivate problem formulation. And on this graph, an example round-robin sequence could be 1, 3, 2, 4, 7, 8, 6, 5. Basically, any permutation of these nodes, right? So let's take two connected nodes here, 3 and 4. As you can see, 3 and 4 are connected. So that means anything 3 sends, 4 can decode. Anything 4 sends, 3 can decode, right? And we have a round-robin schedule, which, just for the sake of example, is 18 slots long. So node 1's transmission, the transmitting node 1 uses 2 slots, 3 uses 3 slots, 2 uses 2 slots, and so on and so forth, right? Now, as you can see, at the end of 3's transmission, right, 4 gets the update from 3. This is simply because 4 is connected to 3, right? Okay. If you now plot the time variation of age at 4 of 3's information, you will see that at the end of 3's transmission, the age is reset to a value of 3. There's this dotted line that basically marks the end of 3's transmission, and you can see that the age is getting reset to 3 at that time instant. After that, it increases as we discussed earlier. In this case, it should increase as steps, not as smoothly though, and it keeps increasing till it again receives 3's transmission. Right? This is the analytic form you get, and the important thing here is that there are two components. One is L3, which is length of node 3's transmission. The other is what we later call the round-robin delay, and it has to do with the length of the round-robin cycle, basically, the round-robin schedule, which in this case is 18. L, right?
Okay. The length of L3, for example, is it a function of the connectivity of that node? Because
no. So length of that's a good question. So L3's, the length of 3's transmission has nothing. Is maybe a function of connectivity in the sense that if you are more connected to other nodes than say an average node in the network, then there is a larger chance that you will end up piggybacking those nodes' information. So for example, if I have a network where you have a hub and everybody goes via the hub, then this hub will always piggyback all these other nodes' information. So this hub's packet size will be larger because it will have more state information piggybacked.
But for now we are assuming there are some numbers.
It's some numbers, doesn't matter. Right, exactly, it's some L3. What values L3 takes will depend on the graph that I showed and also the schedule I choose on the graph. Okay, so look at disconnected nodes. We have 3, 4 and 5. 3 and 5 are disconnected, and the only way, just for the sake of simplicity, 3's information can get to 5 is via 4, right? So at the end of 3's transmission, as before, 4 gets the state of 3, but then this information has to stay at 4 till 4 actually gets a chance to transmit, and that is only after 2 finishes transmission, right? But at the end of 4's transmission, which now will at least piggyback 3's information, 5 will receive the state, basically 5 will receive state of 3, right? Okay, so just to put some notation on this, we again will have the average age will again contain the same round robin component. It will contain what we call the scheduling delay, and the scheduling delay is because although 4, which is the relay, immediately receives the information basically waits or is delayed at the relay till the relay actually gets a chance to transmit it. So that's why it's a scheduling delay, right? And at the end of it, of course, there is this delay that you're always stuck with it, and that is the transmission length of 4's transmission, or the transmission length of the last hop. So if I look at the general, in general, you can actually, your information may actually go via multiple relays, right? In our case, only 4 was the relay. In case you have multiple relays, you basically, the scheduling delay will be a summation of the delays at each hop, right? You're always stuck with the last hop's transmission delay. That's the case in connected nodes and disconnected nodes, okay? And this is between any 2 nodes, U and V, basically. This is the age, the average age. Okay, so if that's clear, what's one of the important insights to take away from this, and that is that even if I assume that even if I have schedules that take the same number of slots, there is a good chance that the system age you will see will not be the same, and that's because the ordering of these nodes in the schedule makes a lot of difference to the scheduling delay, and the scheduling delay itself can be pretty large. So, for example, if I have to go from 4, if I have to go from 5 to 2, I will go from 5 to 4 to 3 to 2, and it turns out the scheduling delay is 25 slots, which is actually more than the length of the round robin schedule itself. Okay. So what's the intuition? Like, why would you want to think of multi-hop in the first place? Why would anybody think that multi-hop can actually do better? And the reason is that if you look at the top diagram for this car network, say the end-to-end link capacity is C, or the end-to-end rate that you can achieve is C, right? Clearly, if you have a multi-hop network, the longest link will probably be smaller, and that basically means that the capacity you can achieve or the rate you can achieve on that smaller link, which is CK in our case, can be much larger than the capacity you will achieve for the end-to-end link in the fully connected network. Now, while that is true, you also have this issue that in case you have a multi-hop network, cars will end up piggybacking more state information than otherwise. So that means that on an average, you will expect larger packets, but you also have this chance of ending up with links that are high rate links. Right? So you basically want to find a rate that can actually offset the large packet size and then give you some gains as far as system age is concerned. Okay, so there is some related work. As I said, piggybacking has been of interest earlier, and one of the biggest differences here is that although they conclude that piggybacking can reduce channel load, which makes complete sense, they however say that the node awareness is reduced, and the reason for that, node awareness is very similar to how fresh information is. They don't use the same metric, but at a node-to-node level, they basically evaluate freshness. Okay, and the reason for this is that they create a multi-hop network by reducing the transfer power. So basically, they are creating a disconnected network by reducing the transfer power, and that basically means that you have, and they are not benefiting from the increased rate as a result. On the other hand, what we do is we create a disconnected network or a multi-hop network by actually increasing the rate at which a node transmits. So we basically benefit from the additional rate, even though we are paying similar penalties because of large packet sizes. Okay, so there's a simple single k-lane n-node network. It's a single lane. Nodes are indexed 1 to n, and the assumptions really are just are not that important actually. So here's the thing. For the general graph, we really do not know what the optimal is. In the thesis there are some insights into what optimal strategies are and what the optimal is for a tree graph, but for a general graph we really don't know. And what we do is we choose a heuristic schedule, which we call the forward and back heuristic schedule. And the idea is very simple. So if you concentrate on node 1 state information, and the schedule is like this. We have nodes 1 to n, and the schedule goes from 1 to 5 to 9 and so on. Remember that the connectivity here is 4. So 1 is basically connected to nodes 2, 3, 4, and 5. Right? So a node I is connected to I plus or minus 4. So basically what 1 is trying to do is it's trying to get its state information through the entire network as quickly as possible. So since 5 is the farthest node that can receive it, 5 should be the next forward. Of course, you cannot achieve this for all nodes, but the forward and back heuristic schedule turns out does pretty well when it comes, especially in comparison to random permutations on the same network. Okay, so with that in mind, let's look at another assumption that we make, which is kind of difficult to implement in practice. It's that if a given node, it always piggybacks the states of all other nodes, okay, the states of all other nodes which are older at its neighbors. So 6 will, for example, in this case, piggyback states of 9, 10, 13, and so on, because there are neighbors of 6 which at whom the states of 9, 10, 13, so on are older than at 6 itself. So 6 knows something new that nodes connected to 6 do not know. So 6 will piggyback all that information.
But how does 6 know whether...
So that's the thing. We make an assumption that 6 knows. So in the real world, you'll have to have a protocol that has some kind of neighbor information, for example, or some additional information which tells 6 what the node should be. So it's a simplification, but the reason why we assume this is also because for any given schedule, this is an optimal assumption. So you're trying to see what's the best you can do. Whether you can do it or not is probably future work. Okay, anyway, so let's go to the next slide. Okay, so this is a slide which is important, and the point being that you have an end-to-end SNR from node 1 to node n for this this network that we conjured up, right? And let that be Q, right? And now since we are creating k-hop connectivity, let the SNR be QK, and you can find QK assuming a path loss model with exponent gamma. This is fairly straightforward and common. And then if you do that, the SNRs, the rates you are interested in are C and CK, where CK is basically a function of QK, which is a larger SNR, because we have smaller links in the network, in the K-connected network, right? And then say C, which is as a result of SNRQ, right? The thing is that your rate determines the slot size. The slot size for the fully connected network is tau, which is 1 by C. For the K-connected network, it is tau K, which is 1 by CK, right? All right. So given this, what do we do with here? So what do we do with this? Given that we have this K-connected network, we want to find the connectivity that is sort of optimal, or in the sense that it gives you the maximum reduction, or it gives you the smallest system age. That's the kind of connectivity you are looking for. Okay, and to do that, we basically define what we call the normalized connectivity. Okay, which is basically a ratio of the K of K and N, the size of the network, right? So anyway, if you go through the math, it's mostly algebra actually, and then you basically end up with this expression. The important thing is that this expression currently is in slots. We still have not associated any slot length to this yet, right? And the other thing is that this is independent of the network size n. So it only depends. The system age basically only depends on x, which is the normalized connectivity, right? Which is a good thing in a way. Right? And now if I basically convert delta to delta in terms of seconds, then basically I get delta subscript tau as a function of the normalized connectivity, and basically I can write the final expression as delta in slots divided by the capacity, which is basically the same as delta into rate, right? Which basically ends up giving you the system age in seconds, right? What we want to do is, as I said earlier, we want to minimize this, and we know, as has been shown in the thesis, that this is independent of n. I'll show you some simulations. All of this math was basically done for large n, but as you'll see in simulations, they are the large n in simulations are of the kind we are interested in. Okay. So the good thing is that I showed all this for a single lane network. It very nicely extends to a multi-lane network. And the schedule we use for a multi-lane network is a concatenation of m single lane schedules. The connectivity is earlier, if you had node 1 in lane 1 connected to nodes up to k plus 1, now all nodes and all lanes, the node 1 and all lanes is similarly connected within its lane, but there's also block connectivity. So nodes 1 to k plus 1 are connected across lanes, right? So the entire block is connected. Similarly, the next block is connected, and so on. Okay, with this kind of a connectivity assumption, you basically see that the optimal normalized connectivity is the same for a single lane network, right? And the other thing you see that, and that's kind of an important thing, and I'll probably say a few more things about this, and that is that the system age is just m times. Remember that the number of nodes has increased m times, and the system age has increased m times. So anyways, as I'll say later, this basically means that all the delays that are now accruing as a result of this increased network are mostly round-robin delays. That's one thing that we show in the thesis. So that's a good thing, because it seems that for this kind of network connectivity and the schedule that we assume, your scheduling delays and all are not really increasing. So in a way, it's a good heuristic schedule to use. Okay, so let's look at simulations. These simulations are not simply evaluations of the analytic expressions that we got. They are simulations that do not use the analytic expressions actually. And what we want to see is that what reductions are obtained in system A, and are the networks, the sizes that we are the network sizes of interest really, at which you get these gains. Okay, and also we will look at what if you do not select the schedule. What if you select any random permutation of nodes to be a schedule? Do you still see any gain if you use multi-hop networks? Right. Okay, so this is a 4-lane network. We did it for different size networks. I'm showing it to you for a 4-lane network. I assume 10 megahertz bandwidth. This is mostly to calculate capacity, which is bits per second per hertz. So we are using 10 megahertz. And your packet your header size is 1600 bits. Your state information size is 400 bits, and you're assuming a gamma of 3. I have certain other values that I've used in the thesis, which tell you how things vary with these parameters. But here, the y-axis is system age, and your x-axis is the connectivity of the network. If you look at the blue plots to begin with, the blue plots are where we use the heuristic schedule, the so-called optimal heuristic schedule, right? No, sorry, the schedule is not optimal, it's a heuristic schedule. And we start with values of Q, that is the end-to-end SNR for a fully connected network, starting from -3 dB, which is a very small value, to up to 9 dB. There are two things to see. If you look at the curve for -3 dB, which is the top blue curve, you can see, one, the gains are pretty large. Okay, you get around 67% improvement over a fully connected network that uses round-robin schedules. Okay, and not only that, the gains you get usually reduce. Say they go from 67% at -3 dB end-to-end SNR for a fully connected network to 9 dB end-to-end SNR. They go from 67% to 20% basically. And the reason why you get very large gains for a small end-to-end SNR is because when your end-to-end SNR is really small, reducing the hop size or the hop length actually leads to bigger gains in capacity. The reason being that capacity is logarithmic in SNR, right? So anyways, the gains are pretty large, and the gains are there even when you use random permutations, which are the red curves. The gains are of course much lesser than the gains you get if you use the heuristic schedule that we propose to you. So yeah, so that's the takeaway thing. So it looks like you can actually gain if you use piggybacking, and if you use piggybacking and multi-complex. Okay, so yeah, so just to summarize this part, piggybacking can lead to significant improvements in age. There is the notion of an optimal normalized connectivity for our chosen schedule. The schedule leads, and this is the interesting part, and that is that the schedule leads to age increasing as O of n, and that's good because that basically means that for this schedule, all your delays are mostly because of the round-robin nature of your schedule, and that's something that you can rectify by assuming some kind of spatial reuse. Like there's no reason to have round-robin in a multi-hop network because there surely can be nodes that can transfer in parallel. So anyway, so this is not something that I have done. So I have more slides, but I'm not sure what the time constraints are like. I have the latest work I'm doing on channel modeling. I can run through them if you want, or I can go to the questions and comments slide. So it is like, John, I'm not sure if you have any time constraints. Anybody here?
We're still good.
We're still good?
Yeah, okay.
Okay. Okay, so I have this slide, but I think we'll just, this goes into what we did with the tree. The thing is, for the tree, we know the optimal schedules, right? And the good thing is that the tree has a very nice optimal schedule, and there's a very nice algorithm that can tell you what the optimal schedule is. But the bad thing is that it's not very useful in anything of vehicular networks, right? But there is one heuristic that we derive, and that can be useful, and That's the second point in the presentation, and that is, if you have this kind of a node, which is a leaf, that is its connectivity to the main network is only via a given vehicle, let's say, right? Then that leaf node must broadcast its state just before the parent node, the node via which it's connected. Okay. Now it's kind of difficult to conjure up general scenarios where this might be useful, but one place this might be useful is, for example, a vehicle that's trying to merge into a highway. So it's not a part of the platoon, but it wants to become a part of the platoon. So its initial connectivity may be limited to a vehicle at the corner of the platoon, let's say, or you might want it only to talk to one of the members of the platoon. So in those kind of cases, this heuristic might be useful. I've not really used it, but it is a heuristic that holds in general. Okay. So after now I'll just give you a brief of the latest work that I did on the effect of vehicles on wireless propagation. So let me just try to motivate this, and most of my work is just assumed interference limited networks. You have a very large number of nodes that interfere if you use CSMA, for example, and I have really ignored channel specifics, but there is, of course, there is a community of people who actually look at better file layer schemes, for example, or schemes that can actually improve reliability in the vehicle-to-vehicle reliability of the vehicle-to-vehicle channel. And the idea is that some part of my work actually that I'll not present today looked at PER and PER, looked at PER kind of statistics, but this part of the work I mostly stick to PER. And let me give you a general overview of the related work. Harris did some work of some specific scenarios that he evaluated. He also did some numerical analysis of various scenarios. There is some very recent work in Mobicom 2010 that did very extensive measurements using DSRC radio prototypes, wherein they basically are interested in packet delivery rate. And one of the differences between their work and the work that I did was, one, we are only modeling the effect of cars on the channel between two cars. Two, we are not using any given radio, right? So we are actually measuring the channel. If you look at the results that they have, they at times get packet error rates of up to 40% for distances less than 50 meters. Like, while I do not know, that's surely not the final radio. The radio was built in 2007, but I think that there is enough scope to improve the file layer when it comes to DSRC. So maybe these measurements will form a small subset of measurements that somebody can use. And okay, so let's get on to it, right? So vehicle-to-vehicle channel cars in vicinity. The idea is very simple. We measured small range scenarios, and we have this receiver, we have the transmitter at the front, and then you can have a few cars which act as scatterers or obstructors, right? And the idea is that you want to measure and model the channel gain. All the scenarios, the transmitter and receiver are always within 50 meters. You have up to 4 scatterers, and you have up to 4 lanes. Okay, so that's the kind of scenarios we're looking. Okay, so this is the basic experiment setup. You have an antenna at the center. Earlier work, we showed that that's the best place to put an antenna if you can. Put it at the center. Otherwise, you end up with more packet errors than you want to. And then, of course, it's battery powered. We have this sinusoid transmitter basically in the transmitter car. And then you have a receiver. I don't think it's very visible, at least not on the projector. And you basically have a spectrum analyzer that basically uses captures the signal over a bandwidth of around 5 kilohertz, which is fairly narrow.
So this is also wide band antenna, right?
Yeah, this antenna covers a long range. Yeah, this is the same antenna that we use, that Harris used. Okay, so let me just explain to you the measurement setup. And the idea behind any scenario that I measured, that we measured, was that you want to capture a given scenario. In this case, the given scenario is you have the transmitter, you have the receiver, and you have these 2 scatterers in 2 adjacent lanes, right? So you want to measure the effect of these scatterers that are in the 2 adjacent lanes over multiple distances between the receiver and the transmitter. Okay. Okay. So basically, the scenario is defined by relative positions of the cars, right? And the way we try to get multiple snapshots of the same scenario is we basically have the receiver traveling at 1 mile per hour and the scatterers at a slightly greater velocity. The transmitter is always stationary, and the reason for that is that we mostly are interested in relative velocities. And since the velocities are pretty small, you are basically measuring the channel in a very fine-grained manner in time. Okay, so the measurement continues, and the receiver moves ahead, the scatterers move ahead, okay, till the scatterers reach the very end, that is where the transmitter is. That's where you pause the measurement, you stop the receiver, and you basically reset the measurement at where the receiver is. So basically you restart the same configuration, but now the receiver is at a different position. And you keep doing this. Sorry. Yeah. So you keep doing this, and that's the entire measurement for this scenario. We did many scenarios, and I think around 20 scenarios. They're all there in the thesis. You had 0, 1 to 2 lane separations. You had, for example, if you look at the lower left corner, you have vehicles that are obstructing the channel. You have cases where vehicles are in adjacent, there are more than one vehicle in adjacent lanes on both sides of the transmitter and receiver, and so on and so forth. Right? And the takeaway was that we tried various models, and it seems that 4 sinusoid models actually give you a very good fit. We tried, even among sinusoid models, we tried 2, 3, 5, and so on. But as far as minimizing error is concerned, mean square error is concerned, 4 sinusoid does a pretty good job. The idea is that these parameters, and we have tabulated them in the thesis, you can use them for simulations, or an analyst can use them for whatever he wants to design over such a channel. So the y-axis here is the gain, the channel gain, and the x-axis is the distance between the transmitter and receiver. And the distances are basically measured using GPS devices that we have both on the transmitter and the receiver. The GPS on the receiver especially was a very accurate device. I think the error was within plus or minus 1 meter. The transmitter was not that great, but the transmitter was mostly stationary. So you have the measured, you have the 4 sign and the 3 sign, and the 4 sign actually seems to track the actual measurements pretty well. Okay.
Did you try 5, by the way?
Huh?
Did you try 5?
Okay.
Is it like getting better if you add more sinuses?
No, actually it isn't. It really isn't. That's why I stopped at 5. I stopped at 4.
Yeah. So one more question is, the measured curve, is it averaged over multiple runs, or it's just
No. So okay, all the points here are okay. So the way the measurement occurs is that measurement occurs over windows. That's how the spectrum analyzer does it. Okay, but all these points are not average. There's no time averaging taking place on these plots. Of course, the models are smoothened versions, so there is implicit averaging in the models. Okay, so this is the summary of how good the power estimation is. And as you can see, there's only one place where you see this many deep dips at times, where the estimation error is pretty bad, in the sense that there are many outliers. Of course, the median is pretty good, and even the 75th percentile, which is the top blue line, these all are box plots in case you are not familiar with them. The top blue line on every box is 75th percentile, the red is the median, and the lower blue line is the 25th percentile. So as you can see that in most cases everything is well within 5 dB. The medians are well below 2 or 3 dB. Okay, so this is power estimation. Let's try to see what an analyst will see when compared to the actual measurements, if the analyst use the 4-sign model that we have. And we basically evaluate, we try to predict the performance and compare the prediction with the actual measurements. We use basically 2 power of m com systems, and we do it for various values of m, as I'll show. And we assume a target BER. The reason is that we are assuming a system where there is some kind of power control, and your application wants to achieve some kind of a BER. We evaluated it for BERs of 10 power minus 3, 10 power minus 4. I'm showing you results for 10 power minus 4. There's not much of a difference. And we assume power control is 4 dB context. The reason being that if you have perfect power control, then you can always achieve this BER. Then the analyst will pretty much always achieve the BER that you want to achieve. Okay. And typically in all systems you have discrete power changes in discrete steps. Okay. So your analyst obtains gains from the 4-sign models. Okay. The system measures the actual channel gain, that's actual measurements. And the question, as I said, is how well does the analyst do? Okay. So this is an example. So for each scenario, you basically do this. For each scenario, you see what both achieve. So for each scenario, both achieve a distribution of achieved BERs, right? The system and the analyst. So these are the BERs that were achieved over a scenario, doing 4 dB quantized power control and using a certain 2 power of m-com system, let's say, right? What you do is you take each one of these distributions. This is a CDF, and the x-axis is log BER, right? Log BER is because we typically talk of BER in terms of 10 power of minus 3, minus 4, and so on. So this is log 10 BER. Right? And what you do is you calculate the differences in percentiles of the BER exponent. So you look at the 25th percentile of what the system got and what the analyst got, calculate the difference. You look at the 75th, 10th, and so on percentiles for the system and the analyst, calculate the difference in the log BER. That's what we are doing. We do this for every scenario. Okay? And then you see what the accuracy in prediction is, and it turns out, as this table actually says, is that the prediction accuracy almost always is within 1 order of magnitude in BER. and it's much better on average. On average, it's actually 0.25 or something. The difference in log P, absolute difference. Okay, so the summary being that the prediction works fairly well.
So from my perspective, what would be interesting to repeat the experiments without scattering cars.
Also,
Transmitter and the receiver, and see how much of the curve you get is from ground reflection and how much is actually from the cars on the side.
yeah, so that's a very good question. So if you have a strong ground component, okay, which you have in many other scenarios, so the region close to 40 meters distance,
Because you have a
the ground component is so strong it doesn't matter what's going on around, unless you have a really big building. So the ground, many people actually, even in simulations, like I remember talking to Dimitri in Bell Labs. So these people had ignored the ground component, no, not Dimitri, but some other people, in very extensive simulations. And they had very nice looking smooth curves, right? Sorry, they had very smooth curves, but they had ignored the ground component in their analysis. And the reason probably was because the ground is so strong that all the scatter is pretty much disappears, right? So the line of sight and ground are the big things, right? But once these scatterers start getting closer to the receiver, for example, or once you get past the 40-meter range, wherein the ground is weaker because of the body of the car itself,
The angle is not
right?
so sharp.
Exactly, the angle is not sharp. Then the scattering makes a big difference. Okay, so yeah, I think you're the only one who has done these kind of measurements earlier. So it's nice to have you here. Okay, so all right, folks. So with that, in summary, right, we basically propose a 4-sign model. There is no real reason for the model. It's just a fit that works really well, and we used it to predict link performance. And at least for these scenarios, the prediction is pretty good. Ideally, I would have wanted a situation where I could actually say whether these models can be used to predict, but unfortunately, we couldn't make those many measurements, or we couldn't come up with those kind of general conclusions, at least in this one. All right, so that's it. I think I'll